Let's revisit the Stackelberg model and figure out what the subgame perfect Nash equilibria are. There are infinitely many proper subgames of this Stackelberg model. Remember that for every choice that firm 1 could make, for every Q1, there's a subgame at which firm 2 must decide the quantity that it would like to choose. So if we go back to the version of the Stackelberg model that we had seen earlier, where each firm has to pick a quantity between 0 and 12, and the price is given by 12 minus the total quantity. For each quantity that firm 1 could pick between 0 and 12, there's a subgame at which firm 2 must decide what its quantity is going to be. The subgame is, in a sense, trivially a game. There's only one player to this subgame. It's firm 2, which must solve its maximization problem to pick the optimal quantity Q2, given the quantity that firm 1 has chosen. In other words, firm 2 solves the following maximization problem. Taking as a constant the choice of firm 1, firm 2 must pick Q2 that maximizes its payoff. The first order condition is 12 minus Q1 minus 2Q2 equals 0. So the optimal Q2 is 12 minus Q1 divided by 2. That's what firm 2 will choose in the subgame. What are the payoffs that each of the firms get after firm 2 has chosen this quantity? Firm 1's payoff will be 12 minus Q1 minus Q2, which is 12 minus Q1 over 2. So if we subtract that from 12 minus Q1, we just get 12 minus Q1 over 2 times Q1. Firm 2's payoff is 12 minus Q1 over 2, which is the price, times the quantity Q2, which is 12 minus Q1 over 2. So it's 12 minus Q1 over 2 squared. Now if we come back to the initial node, we can figure out what firm 1 should choose. Firm 1 is going to choose Q1 to maximize its payoff that would get after firm 2 behaves in this rational way. So it solves the following maximization problem. It chooses Q1 between 0 and 12 to maximize 12 minus Q1 divided by 2 times Q1. So we can solve this. The first order condition is 6 minus Q1 equals 0, meaning that the optimal Q1 is 6. So the subgame perfect equilibrium for firm 1 to choose the quantity 6, and for firm 2 to use the function S2 of Q1 equals 12 minus Q1 divided by 2. The equilibrium path is that firm 1 picks the quantity 6, firm 2 then picks the quantity 12 minus 6, which is 6, divided by 2, which is 3. So firm 2 produces 3, firm 1 produces 6. That's what happens on the equilibrium path. Yet, off the equilibrium path, firm 2 still behaves optimally. So firm 2 isn't making crazy threats of producing these amounts that are going to cause it to even have a loss if firm 1 doesn't produce a specific amount, which is what we saw earlier when we showed that there were many Nash equilibria and we could support as a Nash equilibrium any production decision for firm 1. One thing I want to point out here is that what we did was to write down the payoff that firm 1 would get for every action that it could take. We said this is the strategy that firm 2 is going to play, which is to produce this quantity 12 minus Q1 over 2. So we solved for player 2's strategy in the subgame. Based on the behavior that we solved for player 2 in the subgame, we were able to figure out what player 1's payoff would be as a function of player 1's choice of quantity. In other words, starting at the initial node, we look at each of these, and as a function of the choice of Q1, we were able to write down that firm 1's payoff would be 12 minus Q1 over 2 times Q1. And that's true for every possible choice that firm 1 could make. This here is what we call a continuation value from the choice Q1. So firm 1 plays this action at this node, so as the game continues, that's the payoff that the firm will get. That's called a continuation value. This concept of a continuation value is quite useful when we're trying to solve these types of dynamic games. So at a given node, a player's continuation value is the payoff that that player will get, given that the path of play passes through that node. So let's draw a possible decision node for player I. There's maybe a few choices that player I could make at that node. And that brings us to some other nodes, and the game would continue from there forward. Let's say player I could choose A, B, or C at this decision node. Given a strategy profile S, some strategy profile S, since every player's strategy is a complete contingent plan, if we go to any decision node, we can find a way down to a terminal node from that node. And that's true for each of these. So no matter what choice I might make, A, B, or C, because we've got a profile of complete contingent plans for every player, if we go to this node and follow the strategies in this, from this node forward, we would get to some terminal node. Similarly, from here we'd get to some terminal node, and from here we'd get to some terminal node. We can look at the payoff associated with each of those terminal nodes that are reachable from these nodes, and the payoff that player I would get at those terminal nodes is the continuation value. So when player I is trying to decide between A, B, and C, that's what player I is going to look at. If we have some strategy profile S, and let's suppose this strategy profile was a subgame perfect equilibrium, then it would have to be that player I has to be maximizing their continuation value when they choose between A, B, and C. So given some strategy profile little s, following this strategy profile from any given node, in particular from this one, and this one, eventually leads you to some terminal node. From if you follow it from here, you get to here. If you follow it from here, you get to here. And if you follow it from here, you get to here. Each of these is associated with some payoff. So at a given decision node, this decision node here, for example, following S from any of its successors, so these are the successors, leads to some payoffs. Let's call this P of A. That's the payoff you would eventually get if you chose A. This is the payoff you'd eventually get if you chose B. This is the payoff you'd eventually get if you chose C. These payoffs associated with these successors, so P of A for A, P of B for B, P of C for C, are what we call the continuation values of the actions associated with the node that leads you to that payoff. So for this node, it leads us to this payoff PA, and A brings us from this decision node to here. So if I play the action A and we're in the profile S, then eventually we'll end up at me getting a payoff of PA. Similarly, if I choose B, I'll eventually get PB. If I choose C, I'll eventually get PC. So when we're trying to solve games using backwards induction, for example, calculating these continuation values makes it very easy to then solve for the Nash equilibrium, because we just solve the game down here, and that tells us what the subgame perfect Nash equilibrium strategies would have to do, and therefore which payoff this node would eventually lead us to. They would tell us what this node would eventually lead us to. They'd tell us what this node would eventually lead us to. So if you have the continuation values, at each step, all you're having to do is maximize the continuation value for each player. Remember that if a strategy profile S is a subgame perfect Nash equilibrium, then for every player I, given the other player's strategies, at every node where I is called to play, the action that SI prescribes has to be optimal. That's just by the definition of a subgame perfect equilibrium. What this means is that there's no profitable deviation to some other strategy from that node onwards for player I. That would give player I a higher payoff in the subgame. There is no SI prime that I could switch to at that node, so that in the subgame, player I, rather than playing according to SI, would behave according to SI prime, and that deviation from SI would be a profitable one. So it would give him a higher payoff. And this is what it means for S to be a subgame perfect equilibrium. In order to check whether there exists a profitable deviation or not, do we need to check all possible contingent plans for the subgame? That would be a lot of things to check. It turns out we don't actually have to check everything. It's enough to check what are called single deviations. Some authors call these one-shot deviations. What's a one-shot deviation? As the name suggests, a single deviation or one-shot deviation is a deviation from a strategy that differs at only one information set. So a strategy SI prime is a single deviation of SI if it differs from SI at exactly one information set. What do I mean by that? Remember that since strategies are complete contingent plans, they specify an action for every possible information set where a player could be called to play. So if we numbered the information sets, let's say they're 1, 2, 3, all the way through some k, so player I were to be called to play at k different information sets, we would write down the action that player I would take at these k different information sets. So perhaps they take action A1, A2, A3 through AK, and let's say that were SI. SI prime would be a single deviation if exactly one of these was different from SI. So if we had, for example, A1, A2. Perhaps this one was B3, but everything else was the same. So we had 4 here, A4. Again, we switch back to A4 and A through AK. So they're all A's, except this one information set. In that information set number 3, you play a different action under SI prime than you would under SI. Then SI prime is a one-shot deviation from SI, or a single deviation from SI. Now, why do we care about these one-shot deviations? In order to prove that something is a subgame perfect Nash equilibrium, rather than looking at all possible deviations and showing that none of them are profitable, if you can just look at single deviations and show that there's no profitable single deviations, that's a lot easier to do. And it turns out that is actually enough. Let's look at 2 different strategy profiles. One where player I plays SI, everybody else plays S minus I, and the other where player I plays SI prime, and everybody else still plays S minus I. So consider these 2 profiles, SI S minus I and SI prime S minus I. So there's one information set X where SI and SI prime are different. This information set shows up somewhere in our game tree, and for simplicity, let's suppose that there's only one node in this information set. At this information set, we'll just look at the 2 things that player I does under these 2 different strategies. There's some tree here, there's some subtree here, and there's some subtree here. Under SI, suppose he goes this way, and under SI prime, he goes this way. Now, because these are one-shot deviations, the path from this node to a terminal node is going to be the same under both profiles. Similarly, the path from this node down to a terminal node is going to be the same under both profiles. So the way the game is going to proceed from either of these successor nodes is going to be the same under both of those profiles. This means that the continuation values are going to be the same. So the continuation values of this action and this action are the same whether you're looking at it with this profile or this profile. If we start with a strategy profile that's a subgame perfect equilibrium, then you know that in every subgame, it's a Nash equilibrium, so there's no profitable deviation below. So all you have to check is if there's a one-shot deviation. So the one-shot deviation principle tells us in any finite extensive form game, some profile S star is a subgame perfect equilibrium if and only if for every player I and every information set where I could be called to play, there exists no SI prime such that SI prime is a profitable one-shot deviation of SI star. So just ruling out one-shot deviation at every information set is enough to verify that a profile is a subgame perfect equilibrium.